pile foundation, and the deflection I have told you is composed of two parts. One is caused by the horizontal load PT and the overturning moment. So, if this is your y, so then y is equals to y A plus y B. So, the formulas that I have given you still hold good, that is you write down the equations for deflection. So, deflection, this is your deflection equation. So, this deflection equation, you start from the deflection coefficient A. So, that is A y has already been given as y A, this is y A multiplied by E I, and this is P T over T cube. So, mind you, so these are all non-dimensional coefficients. Okay. So, this is deflection caused by P T, deflection from horizontal load. And the other one is the B y. So, this is coming from the moment term. So, instead of P T you will get MT. So, you non-dimensionalize the deflections. So, this becomes y B multiplied by E I M T T square. So, this is deflection from horizontal load P T, you write this is deflection from M T. So, now you can write down the equation for y. So, y turns out to be, from this you can get y A. So, coming to this equation, this is from 1 we get, so y equals to y A plus y B. Now, y A you get from here. Now, this will be equals to the coefficient, you keep this as A y. So, this is multiplied by P T T cube over E I. So, this is the first coefficient we are getting, plus the other term will be B y, that is coming from the moment. So, this is M T T square over E I. So, this is coming from here. So, now this is your deflection. Now, you find out the slope equation. So, slope is given by dy by dx. So, now you differentiate this equation with respect to x. Now, x has been non-dimensional. I have non-dimensionalized all these terms. If you look into your previous notes, what was the definition for x? So, x was given as the z has been defined as x by t, and t is your I think relative stiffness factor. So, from this you get x is equals to some coefficient z multiplied by t. So, if you want to differentiate x, you have to differentiate t. So, you find out the differentiation for t. So, dy by dx, you write this, the slope that is coming from the horizontal load plus slope that is coming from b. So, you differentiate this. Now, you will get a coefficient that is a s multiplied by, this will be t square, and you keep all the coefficients outside and collect it in a s. Okay. So, that is the way it has been done. So, this becomes E I. Similarly, you differentiate this one. So, this will give you B s. Now, these coefficients will change because you are taking this out. So, this will be how much? M T T over E I. So, this we have got this slope equation. Now, you find out the other terms, that is the bending moment. Now, all these are coming from the equation for the bending of the flexural deflection of a beam. So, pile has been taken as a vertical beam and it is being applied as a point load on the pile head. So, bending moment equation is how much? So, you remember all this, huh? EI d square y by dx square. So, this you correct the constant terms. Now, bending moment is also of two parts, MA plus MB. So, now you write down the equation for bending moment. So, the slope equation you have to differentiate. Slope equation we have got in terms of t square and t. So, another constant will come out, say these coefficients you can write this as the subscripts, S is denote for slope, Y for deflection. So, your constant you write this as AM. So, this will be AM. Now, you tell me what is inside the bracket. So, you simply differentiate this. So, differentiate of the slope and that EI you will correct in the constant. Okay. So, you differentiate how much it comes. So, this will be PTT, isn't it? The constants are corrected and kept in AM. The other term, I differentiate this term with respect to T. So, this is simply MT. This you correct in the AM coefficient. So, this is coming out to be how much we are getting, BM multiplied by MT. So, these equations are simple, just you have to remember how they have been differentiated. So, this is the equation number 1, we are getting the deflection equation, then 2 we are getting the slope equation, and 3 we are getting the bending moment equation. What else is left? Shear. Now, shear is given by, this is EI d cube y by dx cube. So, similarly you differentiate this equation, you get the shear equation. Now, shear is given in terms of V. So, this is equals to VA, shear caused by the load and the shear caused by bending moment. So, the previous problem we worked out the maximum, the axial load and maximum shear. Now, so this is will be equals to how much? You differentiate this with respect to 2, you simply get PT, and there is another constant will come. So, this will be PT, but differentiate MT, what you will get? Here there is no T. So, this is T to the power 0, isn't it? Now, T to the power 0, actually this should be 0, but you keep it like this in AV and BT terms. So, this if you differentiate, it will be sorry, no, there is no dot, by mistake it has come here. So, this is MT by T minus 1, it will come minus 1 is divided by T, 0 if you corrected, the constants are actually corrected in BV. This is T to the power 0. So, 0 into BM you get 0, but he is, since you have split up into caused by the shear, the lateral load and the moment, you write in this form. So, this becomes T to the power minus 1, you keep it above below T. So, this is how it has done it. The last one is your soil reaction. So, instead of vanishing the constant, you keep this in BV. Now, again you differentiate this. So, soil reaction is given as P. P is equals to PA plus PB. So, again differentiate this. Same thing. No, you keep, imagine this to be T to the power 0 and differentiate this. So, this will be AP. and t to the power 0, if you differentiate, becomes t to the power minus 1. You take it outside and collect it in the constant AP and BP, and this one will be mt by t square. So, this is equation number 4, equation number 5. So, this is the vertical or this is called laterally loaded. This is the simplest case we are analyzing for a single pile. Now, in this equation, I have already given you the formula for this relative stiffness. So, the other terms are the subgrade modulus is ES. ES we have worked out to be NH, sorry, this is not eta, this is N, and this is x to the power n, and from this you can calculate the phi z. So, phi z has been defined as this is soil modulus function. So, this is ES multiplied by t to the power 4 over EI. Now, this work was done by two gentlemen called Rees and Matlock. So, this is called Rees and Matlock. Now, this we have to simplify. So, you substitute this. ES is NH x to the power n. So, from here we are getting phi z. If you substitute this, we will get NH x to the power n t to the power 4 over EI. The soil modulus function. Now, so phi z comes out to be, and the relative stiffness factor has been defined as what? Now, T has been defined by EI over NH to the power 1 divided by n plus 4. So, these are actually empirical formulas which has come from your the soil mechanics. So, this was carried out by Rees and Matlock. So, now you can write down what is the equation for phi z. So, you simplify this equation. Phi z you substitute this. So, this becomes how much? NH over EI T raised to the power. So, this will become x to the power n t to the power 4 is divided by t raised to the power n plus 4. So, we are getting x by t to the power n. Now, what is this x by t? X by t is nothing but the z, that is your depth coefficient. So, phi z works out to be the depth coefficient to the power n. So, this you remember. So, this is the formula for soil reaction, this is important, and the equation for phi. Now, let us come back to the partially restrained pile head which we were analyzing. Now, if you look at the jacket platform, say this is the pile. So, pile has gone inside the jacket. Actually, I should have drawn a dash line. So, this is your offshore pile. Now, your jacket actually is a cover for this pile. So, it will go like this, and mind you, this is occurring below the seabed. So, a portion of the jacket is gone down below the seabed. Now, at this juncture, you will have all these bracing members. Now, here you get your that plate that is called the mat will come somewhere here, which I have not drawn. So, these are your bracings. So, we are just looking at the jacket, part of the jacket which has gone down below the seabed. The other portion this is extended. So, this is your seabed. Now, the jacket, I told you we are analyzing this as a, what was the type of pile? This is called pile head, restricted against rotation, or partially, I have defined earlier, this is partially restrained pile head, the type of pile that we are analyzing. Now, this has special partially restrained pile head. So, this is pile head restricted against rotation. Is rotation by what? By jacket. Jacket is the restraint. So, there is the offshore column pile. So, now if you apply, say let us apply a load, the pile is going to bend, but it is not free to bend. So, there will be a restraint coming on the pile, and it will go like this. The deflection curve of the pile, of course, this is a very enlarged case, it will try to go like this. So, this is a pile head restrained by the jacket. Now, at this point you will get a slope. So, there is deflection as well as rotation. This slope, you mark this as S T. So, I am writing this as slope. Now, we will employ this same slope equation. The slope equation that we have derived is this one. So, we will try to use this in our analysis. Okay. Now, what we are getting at this juncture, suppose your wave load is coming at this point, so you will be getting actually one moment at the seabed. So, this is your MT will come, and obviously the load will come here. So, this is called your pile head load PT. You take this at the seabed, there will be a couple as well as a horizontal force. So, this is the situation. Now, if you want to analyze this kind of pile, there is another factor which you should know, it is called the relative stiffness factor. So, this is defined as the moment divided by slope ST. So, K theta is called spring stiffness factor. Now, you write down the slope equation in terms of this K theta. So, what was our slope equation? So, this was the equation for the slope. Now, you substitute K theta. So, you are getting both MT and PT out in the slope equation. And you collect all the terms in the moment, that is your MT and PT to one side, and see what you get. So, our slope equation is now you try to bring this K theta term inside. So, ST is how much? ST is given as K theta by this is MT by K theta. So, you take this outside. So, sometimes you will get and divide by PT. You simply put ST equals to MT by KT. Now, you collect all these terms. So, this side we will get MT is PTT K theta. So, now this comes to be how much? Now, any further simplification we can do? Now we are left with this term. This is 1 by k theta. I try to bring this outside. Then you have to multiply this thing by, this will be minus bs k theta, and t will come out here. So, this will be I. Am I right? So, multiply these two. So, you are getting empty, your t will cancel. Pt, this is okay, huh? K theta will come. K theta I have kept here. Also, k theta empty pt k theta empty, yeah, and this is k theta shouldn't be there. So, this empty and pt we have kept it outside. K theta will not be there. So, now it is okay, no? So, this will be as t over ei. Now, any further simplification we can do. So, now it is so ultimately we have got this. So, what is the equation for MT? This one. So, your ei is going to cancel on both sides. So, this will go on the right hand side, we will be getting, this is as t we are getting, and k theta will come, as t k theta will come, and the denominator we will get ei minus bs k v theta, this is bs k theta t. So, we have finally succeeded in isolating this term. Now, you write down your deflection equation. What was your deflection equation? You see at the equations that I have given you, what was the equation for y? Y we have written as ya plus yb. So, that same equation again you write in terms of this term. So, y equation becomes AY, this is PT T cube. Now, all these coefficients, that is your AS, AY, BY, you get in form of a table in recent MATLAB. Otherwise, you cannot find out the y slope, deflection, moment, you cannot find out. Now, in this equation, you try to bring this factor. So, this factor if you want to bring, then you have to make some correction. So, this becomes how much? MTPT by T. So, you write y in terms of a coefficient Cy multiplied by PT T cube divided by EI. So, then what is Cy? So, y if you put in terms of a coefficient Cy, then you have brought this out. So, y becomes equals to now inside you are getting AY plus how much? What will be this? So, By will remain as it is, isn't it? Now, since you have this is PT, so you have to divide by PT. So, this is divided by PT and PTT and on numerator. So, now it is coming, PT will cancel, this will become T square MT and you are getting EI. So, now we have somehow brought this term inside our deflection term. So, then what is this? So, this is your Cy, or you bring this in terms of a coefficient and keep this factor out. Now, similarly, you write down the moment equation. So, this is what we are getting. This is equation number 5, I think. Now, you write down, or this is 6. Now, write down the moment equation. So, moment equation you try to bring another coefficient. So, moment equation, the formula that I have written, where is that? Yeah, that bending moment equation. So, your moment equation, you write bending moment M is, or rather it is written as MT, whatever it is. So, this is AM PTT plus BM multiplied by MT. Now, you try to bring out this factor again, MT PT over T. So, this one is simple. Huh? So, bending moment comes out to be M. If you take this PT over T out, then inside you will get AM plus simply this BM multiplied by this MT over PTT. So, in both cases we have succeeded in bringing this term out. So, this is your CM coefficient. So, we are getting the two important parameters One is the deflection we are getting in terms of a coefficient which is called Cy multiplied by Pt T cube over Ei. So, this is one important relation we have got. The other important relation that we have got is the bending moment term. So, this is simply Cm multiplied by Ptt. Now, these two equations we will use to find out the, so this is equation number 7, this is equation number 8. So, these two equations you remember, the deflection and bending moment equations, and the coefficients of Cy and Cn. Now, if you plot a graph, you will find you plot Cy along this axis and you plot Z. And you will get a series of graphs. So, this starts from, say, let us, you take the axis starting from 0 0 and this will go up to say half, so this is 0.5, and this one somewhere you will get 1, then you will get say 1.5 will come somewhere here and ground will be 2.0. So, these are values of your Z coefficient. Now, you plot Cy, so Cy you will get 0.5, this you will get 1.0, this is 1.5, this is 2.0, this is 2.5. Now, you get a series of graphs like this. It starts somewhere around here. Now, you plot this for various series of values of this MT. That is why we have brought this thing out. In both the coefficients Cy and Cm, you will find MT Pt over T. So, these are actually a non-dimensional coefficient. So, this you plot against values of this. Now, for a fixed head case, what it should be the value of St. You will get a range of graphs like this. It actually comes somewhere here. Anyway, in the book, and this at the end you will get, this will become like this. Now, the outermost one is your free head pile. And there will be another line which will be somewhere here. Now, these set of curves are various values of this ratio. So, these are values of MT over PTT. Now, if you want to use this graph and to find out this CY coefficient, so that means your range of values should lie between the free head pile and the fixed head pile. Now, free head pile, your definition, free head means in this case the value of MT should be equal to 0. So, that means there is no bending moment. Fixed head means ST equal to 0. So, these are the two limits. Now, in between you have to find out for these values of MT by PT at a particular depth your CY value. Now, once you know CY, that means your deflection is known. So, this CY value, if you know, the PT, T values, all these other things are known, isn't it? So, immediately you can calculate Y at a particular value of Z. The Z is equal to XT. So, this is actually not giving in terms of X, this is giving in terms of Z, that is your non-dimensional coefficient. So, this we can find out the pile deflections. So, this is actually a this is given in Rees and Matlock 1961. CY, but in this case EX to the power n, CY for lateral loaded pile followed. But in this case the ES formula that has been used is NHX. This one has been taken as 0. Now, 0 is for what type of soil? There are types of soil I have told you. This is cohesionless soil, I think. See, n equals to 0. It is not mentioned, I think. No, sorry, n is equal to 0 you write for stiff clay. So, he has taken this for n equals to 0. So, that means stiff clay has been taken. So, this set of graphs you will find in Rees and Matlock. Now, another set of curves can be drawn, which of course he has not shown here, for n equals to 1. So, n equals to 1 is granular. Granular means sandy soil. So, this is how you calculate deflection. Now, how do you calculate the bending moment? Bending moment equation. That you have to know the value of Cm. So, bending moment equation we have derived as m equals to Cm PTT. Now, a set of curves have to be drawn for Cm, the moment coefficient. So, again you will find so once you know Cm, you can calculate the bending moment MT. but Cm again depends on mt pt over t. So, here you will get, now this stretches from minus 1.0, this is minus 0.8, minus 0.6, like this it goes up to plus 1.8. Now, your 0 will come somewhere here actually, and you will get a set of curves, and this is your z value. You get another set of curves like this. Now, you have to fix the two boundaries. One is your fixed pile head, fixed head, and the free head case. So, depth coefficient z, you start 0 from the top, here it is 3.0. So, like this you go somewhere here, this will be 1. So, this is 2.0 and this is 3.0, and here you get various values of this one, mt pt over t. Followed. So, this will be from minus 0.93. So, this is what? This is your fixed head case, fixed head pile. So, most of your calculations will lie between this line and your free head pile. So, this is fixed head. And free head values you will get, free head will be coming to 0. In our case, what we have defined, the same thing I think we have given this as 0 also. The other set of curves that we have drawn, your free head is mt equal to 0. So, obviously, this is going to be 0, isn't it? So, free head is coming somewhere here. This is the value of, say, mt pt t equal to 0. So, obviously, this is your free head. Fixed head pile. So, most of your values will lie between this. The other values are not bothered. So, once Cm is known, that means you can calculate bending moment. So, bending moment and deflection you can get. So, after you have got the bending moment, then what else can you do?
Dy is equal to Ay plus By into mt by pt into t. There we can substitute t is equal to x by z.
Z is equal to that z by t, x is equal to z by t.
Z is equal to x by t.
Is it? How much? What we have definition of z we have given? Z is that x by t.
T is equal to x by z.
No, t is not that. That t is coming from. Of course, that will be there. Now, what is the problem actually? T is the relative stiffness factor here. T is x by z here. You simply remember this has been done with respect to z. See, this value, this mt, MT PT T. So, this is the most crucial factor. And MT is what? This you have to calculate. This is coming from your wave load. PT is horizontal wave load. So, what is MT? MT is PT multiplied by lever arm straight away. Now, this T is actually varying with respect to this the EI is your this is called the pile rigidity, and the other value, that is your NH term. Now, NH term, if you want to get, you have to derive it from the ES value or modulus of the soil. So, T is actually linking your soil with the pile in this term. So, here now all these are known values. MT you know, you are getting it from the horizontal wave load moment. PT is your the horizontal load, T is known. So, in both the equations of M and Y, this value is known. And no, in the set of graphs, actually what he has used is these AY and BY and AM and BM values. Now, this actually is given in tabular form in the RIS and MATLAB. You can use the tables, or if you do not want to use the tables, you consult these graphs. So, this part is known and also the coefficients are known. So, now you can calculate your Y and M straight away. Now, the reason that we have calculated Y is the sometimes they have a limit on deflection for pile. Pile deflection, there is limit, you cannot keep on deflecting the pile according to your load, otherwise it will break. So, most of the classification societies, they have a limit on Y, and from this M you can calculate, once you know the bending moment, you can calculate bending stress. Now, how you calculate bending stress? Sigma bending is bending moment divided by I by Y of the pile. This is right or wrong? And the same thing as in your ships you have calculated. So, same thing will come out here. So, here we are calculating the limiting stress which is coming from bending, once you know the I by Y value. Your pile is actually behaving like this thing, a column or a beam with a point load. The load is coming at the head, actually this is how it is bending. So, the only problem is the action is taking place below the soil. The soil reaction is coming because of this NH. Anyway, so we stop here, and after this we will you have some knowledge of this thing.